Okay, now we begin with intermodal dispersion. Increase in pulse width due to propagation variation in the propagation time of different modes at the same wavelength. So what this highly complicated statement means is you have a beam of light. You assume that every ray in that beam has the same wavelength. So looking at intermodal dispersion, so what it says is you have a beam of light which consists of multiple independent rays. Now to refer to each ray, we are going to use the term modes. So when I say different modes, I just mean that I am talking about the different rays which make up that beam. Each of them has its own phase. They all have the same wavelength, but the phase is different for each of these individual rays or modes. Ray and mode are interchangeable terms. So what happens is variation in the propagation time of different modes, meaning each mode travels at its own speed. Instead of the entire entire beam traveling at one uniform speed, each ray in that beam is going to travel at its own speed. So one of them reaches the end very fast, one of them slows down, and so on. So finally your receival time is going to be delayed because of the slower ones, and that is what we mean by the way of slowing down or increase in pulse width. So we'll understand better when we look at this diagram. So we have a ray of light, and one of these is incident at this angle, this dark blue ray. The other is incident at a different angle. So depending upon the angle at which they were incident, and that is what I mean when I say they have different phase. So each one of them travels in a different path. So each one of them is going to reach at a slightly different time. The time difference is going to be of the order microseconds only, not more than that, but still every wave does not reach the end at the same instant. So there is some speed up, some slow down, and that is what we call intermodal dispersion. Why intermodal? Because we are talking about different modes at the same wavelength. And then we move on to the second type of dispersion, which is called chromatic dispersion or intramodal dispersion. So what we assume here is we have a beam of light again, but let's assume every ray or every mode is traveling at the same phase and hence same velocity. So there is no difference between the velocities of the individual rays, but each ray has a different wavelength. So because the wavelength is different, the velocity is going to be different. So some of them are fast, some of them are slow. So some reach earlier, some reach late, and eventually the entire signal is delayed. So you might ask me why we have different wavelengths when we have only one light source. That is because even if you have a single source of light, it is not possible to generate light at just one frequency. So those of you who attended the Google Meet where I was explaining acoustics and ultrasonics, you might have heard me tell you this. No source of sound in the world produces sound at a single frequency. You have a fundamental frequency, but the sound will always be a range of frequencies. So if my fundamental frequency is 100 Hz, I might be speaking at a range 90 to 110 or 95 to 105, something like that. So it's the average frequency is what we call the fundamental frequency. It is not that every sound wave coming from my sound box, from my voice box is at 100. That's not the case. Similarly, even though you take a laser or any light source for that matter, it has a fundamental wavelength which is the central or the average wavelength of the light waves it generates. But that does not mean every single ray it generates has this very wavelength. There is a range again. So let's say my wavelength is 1500 nanometers. There will be some waves which are like 1485, 1490, some which will be 1505, 1515, something like that. So those minute differences, those differences are of the order nanometers. So for us it's negligible, but because of those minute differences in the wavelength, the velocity is also affected. So there will be a time delay or a time speed up between different rays. That will again be of the order microseconds, but still there is a discrepancy in the time taken by ray 1 and ray n to reach. So your wave is getting slowed down. That is chromatic dispersion. It happens among waves of different wavelengths but the same phase.